It's live on Facebook.
Okay, it's 11 o'clock on a Sunday morning, which means it's time for Chai and Why. Today is actually the beginning of our summer specials. And we really miss having all of you either at Prithvi Cafe or outside at Rupa Rail in the open, doing experiments with kids of all ages. We've had, young kids, big kids, old kids, everyone very eager to do hands-on experiments. But we're trying our best to bring you something at least online. And today is actually a great day to start because May 16th is the International Day of Light. This is a United Nations Day which celebrates the fact that light and technologies using light benefit humanity. Just to give you two examples. If you're in India, or at least on the west coast of India in Mumbai, you know that there's a cyclone outside. How do we know it? It's because we can take pictures from satellites. Not just take pictures. We even have the ability to look at the light that's coming out, and we can tell you that the cloud top temperature a few hours back when I checked was minus 93 C. We know how tall the cloud is. Depending on the wavelength or the color of light we look at these clouds in, we can see how much water they have, how much water vapor there is. We know how much rain there will be. That's one thing, large scale. In the COVID crisis, the one instrument that's most in the news is a pulse oximeter. It's something you put on your hand, you put on a finger, you can measure the amount of oxygen. That depends, again, on shining two colors of light through your finger and looking at this very small differences in color between oxygenated light, blood, and non-oxygenated when the oxygen levels differ during the pulse, and you can actually measure how much oxygen there is in the blood. Isn't that amazing what light allows you to do? Right? So let's celebrate light today. That was the theme of the day. And in fact, this weekend, May 15th, 16th, especially for Mumbai, is actually very special for another reason in light. It is what is called Zero Shadow Day. So if you are between the equator and the Tropic of Cancer, the sun is vertically above you on 2 days in a year. While it's going up, it's May 15th or 16th, 16th in the suburbs, 15th if you're in Kulaba where we are. And when it's going down, it's again around July 27, 28. That's typically in the monsoon. Well, today should have been a perfect good day, but because of the cyclone, it's cloudy and it's anyway zero shadow since morning. So maybe we won't see it, but we will try at around 12:30 if we can. We have somebody on this call from Kalyan. If he can, if he has sun there, we will try and see if we can see the zero shadow thing also. But anyway, let's get started. So this time we've arranged for experiments, of course, using light. We will start off with light. And in fact, there are just so many experiments with light. There are just so many experiments that we won't be able to finish them today. The next session 2 weeks from now is also going to be much more light experiments. Today's a simple light experiments. We look at more fun things with more energy, more polarization, etc. We'll do lots of fun experiments with light. Then, of course, we will move over to chemistry experiments, some things in mathematics demonstrations, biology. We will cover everything over the next month or two. It's going to be fun. Do join in. But remember, it's online and we need your feedback. So please type in your comments and questions in the chat box on the Zoom webinar or on YouTube or Facebook, wherever you're watching. And with that, I think it's time to introduce today's team. When you talk about light and optics, it's basically all about we thought, let's get our students. The IFR has a chapter of the Optical Society, and we have our volunteers with us. There is Himadri. Himadri is a third-year student who works on nano optics. There is a Parajit. Parajit does high power, ultra high intensity laser kind of work, and they are going to be helped with Ankit, who's hiding somewhere over there, and Kiran. And where's Kiran hiding? Kiran is hiding somewhere here. So Ankit and Kiran are also going to help them. All students, I'm going to step back now. I'll be monitoring questions on the Zoom and Facebook and YouTube. Keep your questions coming. We'll try and get them, and enjoy the show. Of course, we have experiments for you to do at home. So if you're at home and you want to join us, you can do some simple experiments. One of them is going to require just a glass. Just get yourself a glass and a piece of paper and a pen or something. That should be good for one experiment. There are some more experiments for which you might need a bottle, and I'll explain this a little later. If you, of course, have a laser pointer, either a green or red or whatever color laser pointer, you can actually do many of the experiments we are doing. We're not using any fancy lasers. All we are using are standard laser pointers. If you have a green or a red laser pointer, you can do many of these experiments with a laser pointer. So enjoy. Himadri, all yours. Let me transfer the mic to you.
So, hello everybody, I am Himadri. I'm from NOMOL, Nano Optics and Mesoscopic Optics Lab, and today I'll be taking you through some exciting demonstrations on light. So before getting into the demonstrations, of course, we should know what light is, because we have been immensely using it. It's like it's everywhere, right? That's how we are able to see. So basically, in short, we can say that light is the connection between us and the universe. I mean, when you look at the sky at night, there are stars which are sending us light from billions and billions of years ago. So we're essentially looking at the existence of the universe through the window called the sky. Now, when the question comes is then, what is light? Like, can people given in comments like what light is? What do they think that it is? So that we can maybe explore that part, and let me know if, what comments we are getting in. What light actually is.
Source of energy is one of the things.
Okay, good. Yeah, light is a source of energy. Yes. Are we getting any more variations in this part? Any more answers? Any more guesses? Solid, liquid, gas? Okay, fine. So basically, light has multiple facets of its personalities, and I'll be telling you three main. First being that light is the smallest quantity of energy that can be transported. Second, light is a photon, which is an elementary particle which can only be created and destroyed. It doesn't have its own mass. It doesn't have a definite shape. And the third is that light is an electromagnetic radiation, which is a part of the electromagnetic spectrum. Now, what is electromagnetic spectrum? Electromagnetic spectrum consists of a range of wavelengths. Now, what is this wavelength? Let's just find out what wavelength is. So when I say a wave, what picture comes to the mind? So basically, you can focus here. Yeah. So you must have seen water waves, which looks like something like this. So this is how a typical wave looks like, right? It has got these peaks and these valleys, right? So when I say wavelength, wavelength corresponds to the distance between two peaks. This is called the wavelength, which is denoted by the Greek letter lambda. Us in physics, we really generally prefer writing symbols using Greek letters. And yeah, so this is the wavelength. And then we have another concept which is called frequency. Now, what is frequency? So frequency, if you look at this wave here, I said that this is one wavelength, and this one peak to one valley, this corresponds to one cycle, right? So frequency refers to the number of such cycles made in 1 second. So basically, this cycle is given by t, and it is given by 1 over f, or f is equals to 1 over t. So the number of cycles per second is called the frequency, right? So depending upon what the wavelength is and what the frequency is, we have a spectrum, which is called the electromagnetic spectrum, and it looks something like this, and it ranges from, if you look at the it ranges from 1 kilometer to very, very small, like 10 to the power of minus 18 meters, right? And out of that, the visible light is a very small part. As you can see here, the visible light is a very small part which ranges from 400 nanometers to 700 nanometers of wavelength. Okay, now when we talk about visible light, now what is so special about visible light? Is there any speciality? I mean, why are we able to see the visible light only? Any guesses? To tell you simply, the fact lies, actually there is no speciality. It's a coincidence because, as you know, the life essentially started from water. So the first eye that was ever created for an organism, that started in water, and water happens to propagate these electromagnetic radiation at this wavelength, which is the visible range. And hence we were able to get this as you can say that that's why we are able to see this range of light specifically, since that's how our eyes were developed, right? Now, given that fact that we have this visible light and this is the electromagnetic spectrum, and so basically when we talk about light, it can be microwave, it can be radio wave, it can be x-rays, all these correspond to light. Now, how does this electromagnetic spectrum look like, right? So we talked about wave, and now this is how the electromagnetic wave looks like. So as you can see here, you see this red profile of the same wave.
Experiment दिखाएंगे ना हमको?
Of course, of course, of course. थोड़ा bear करो basic का, उसके बाद हम मस्त experiment करेंगे. Right. So fine. So this is the electric field in the red, and there is this magnetic field in the blue, and this is propagating in this direction as marked by this arrow. And this is how the electromagnetic wave travels. Right. Now, based on all these, we will come to the next question, which is what is the speed of light, which I think probably everybody knows. So of course, the value is 299,792,458 meters per second to be exact. Now, the fun part about light is now it is the fastest entity in the universe. But at what? Now, can you tell me, is the speed of light same in air, water, and glasses? Just yes and no would be fine. I mean, let's see. Is the speed of light same in all media?
Okay, the answer is coming in a no.
Great, awesome. Oh, there's one yes as well. Okay, cool. So yeah, most of you guessed it correctly. So yes, actually the answer is no. The light speed differs according to varying media, and the answer why is that is because of something known as the refractive index, or the angle of or the index of refraction of a media. So what happens is essentially when light travels in a medium, so if you look at this, this is a ray of light, and then there are two media here. One is the material one N1 and one is N2, right? And this is a higher refractive index and this is the lower refractive index. Now, as light is incidented towards the other medium, this is the normal to the plane, and we see that the light is refracted towards the normal as it enters from a lower refractive index medium towards the higher refractive index medium. In the opposite case, when the light travels from a higher refractive index medium to a lower refractive index medium, it goes away from the normal. Now, based upon this, so I'll show you.
If this is air and glass, which is higher and lower?
Yeah, so in case it is air and glass, then the lower refractive index would be air and the higher refractive index would be of glass. In the same way, if it is water, then water will have a higher refractive index compared with the air. Okay, now based on this small explanation, we will jump to the first demonstration, which all of you guys have been waiting for eagerly. So let's do it. So here I have two beakers. One is very small, as you can see, and one is very big. And here I have some vegetable oil. Vegetable or any like refined sulfur, whatever you have, you guys can use that. I'll just keep these.
This is a rather messy experiment, which is why we didn't recommend that you all do it at home. But if you have two glass, a small glass and a big glass, you can do it at home. You need some oil, and just make sure that you're going to make puris or something else. You can use a lot of that oil because you don't want to waste the oil. But this is a fun experiment.
Yeah.
So can you see two beakers?
So yeah, so we have 2 beakers here. So now what I'll do, I'll place this small beaker inside the bigger one as such. Right. Now we have this vegetable oil. And now I'll start pouring the oil and let's see what happens. Any guesses what would happen? As I go on doing this, you guys can maybe guess what will happen to the smaller beaker. Will it float or will it maybe, I mean, well, we are not doing chemistry, it might not change colors, but yeah, let's see.
So that's some sunflower oil or something you have?
Yeah, so this is sunflower oil, refined sunflower. So any kind of transparent oil. So now see, we have put the oil up till the brim and now I'm letting it overflow, right? And let's see what happens when it's overflowing. I think I'll stop at this point and I'll show you the profile if you can see. Okay, fine.
Yeah, it's okay.
See, so now I'll just submerge it. I think you can already see what's going on here. Okay, so whoa, where did this go? Where did the beaker vanish? What actually happened? Any guesses? What has happened to the beaker? Or if people are doing the experiment along with us, then you can see if the same thing is happening in your case. I'll do one thing. I'll remove off some extra oil from the surrounding. Do you see the brim?
Yeah.
Great. So here we can just see probably just the brim of the small beaker. And okay, I'll remove some more.
Yeah, you can see it more prominently now.
Yeah. So now I think the edge is more prominent now, and we can see that we only see the brim of the beaker and not the entire body of it. Now coming to the explanation of why we are seeing this. As I told you earlier, I just described you the concept of how light travels when it goes from a higher diffractive medium to a lower refractive medium. But in this case, what happens is basically, if you compare the refractive index of a glass and the oil, such as the vegetable oil, they have similar refractive index. So in that case, instead of the light going, say, diverting from the normal towards left or right, it rather goes in its own original path. Because of that, we are unable to distinguish between the boundary of the glass when we pour oil inside. But when it had only air, now the refractive index of air and glass are different. That's why we were able to clearly see the boundary of the beaker when there was no oil poured in. So this is what the vanishing beaker has as its explanation. Now moving on to the next, which is another very good explanation to how refractive index works, and that is the experiment of a vanishing arrow, which you guys can do along with us. For this, all you need is a glass, and then you can just draw an arrow on a piece of paper and hold it.
So here's an arrow on a piece of paper that we've drawn and just stuck here. And here's a glass, it's empty, nothing in the glass. So can you see the arrow? Yeah. Okay, so you can see the arrow through the glass. Yeah. And now Kiran is going to pour water in the glass. And this hopefully you can also try at home. Hey, what happened to that arrow?
It wants to go back home. That's the way the exit.
It flipped direction. Yeah. Let's make sure. Let's move the glass out. Look, the arrow is pointing to the left. But when you view it through the glass, the arrow is pointing to the right. So question is, how did the arrow flip its direction?
Yeah, so coming back to the...
If you want to repeat this experiment once, we can repeat the experiment. We toss the water out. There's lots of water, no problem. So you should always repeat experiments to make sure that they're correct. Okay, there we go. You can see the arrow pointing to the left through the glass. And there we go, water. And the arrow has.
Now, why does it enlarge in length? It flipped the side, but it also got enlarged.
That's a nice observation.
Yeah, indeed it is.
You know, there are things which enlarge things when you look at it. I forget what they're called.
Yeah, what is it though?
It depends.
Lenses, no?
Yeah, it is lenses.
Magnifying glass.
Yeah, magnifying glass, which essentially have lenses in them. So I
Glass of
think
water is behaving like a magnifying glass.
absolutely. So basically the glass of water in that is behaving as a magnifying glass, and I'll show you in a bit how it is. But before that, I also wanted to show you, instead of a glass, you can also use a plastic bottle. And we see that the arrow flipping only occurs like, can you see the flipped arrow?
Yeah.
Right. It now what would happen? Will the arrow flip if I position my bottle horizontal?
No, wait, that's too far.
Cool.
Yeah, this way.
Yeah. Now we can see that the arrow is flipped for the bottle as well. Now what would happen if I put it horizontally?
Aha.
Is it flipping?
Aha. Not flipping.
It's not flipping, right?
No, this is fun, isn't it?
Yeah. So what is going on? I mean, what if, yeah, I mean, is it just the water? Is it the bottle? I mean, what is actually
So let's
good?
just make sure people see this properly again. Remember that you had the arrow, we kept the glass of water, the arrow flipped and went to the right. Okay, that is with the right. Okay, now if I do it with a bottle, and this is nothing but just a bottle of water, can you see the bottle of water? Yeah. If I hold it vertically, yes, the arrow which was pointing to the left flips. But if I keep the bottle horizontally and look at it through the water, it's still pointing to the left. So now that's your homework problem. Why don't you try and think about this? We'll let you know the answer at the end if you like, but maybe you can think about it and find out, hey, look, there's no magic in this. This is only science.
Yeah.
So what's going on?
I mean, at least I'll give you the.
Okay, Himadri is going to give them a hint.
Yeah. So I'll give you the not the entire explanation, but I'll just show you the probably a small gray diagram towards why we have this arrow flipping. So here, if you look at the cross section of the bottle, it appears to be like this. It's a circle, right? When we are keeping it upright. And now we have an arrow here. Cool. Now, the light ray coming from this arrow head enters the bottle here. And from here, it enters to the bottle. Now, our bottle has water inside. So, as I had described before, the light would bend towards the normal because we are entering into a higher refractive index medium. While exiting, it will bend. This is the normal, so it will bend away from the normal as it exits the bottle. And now here, what happens? Now this position of the arrow, it appears here and the other end appears here. So this is why we see the flipping of the arrow. You may think why the flipping doesn't occur in case we place the bottle horizontally. And you may give us the explanation to that. That I won't give, that is the homework for you. Cool. So now this was a very cool experiment regarding the refraction of light when it enters from from a higher denser medium to a rarer and a rarer medium to a denser medium, how it works. Now we will move on to another very interesting experiment, which is known as the total internal reflection. Okay, before moving on to that, I'd pose some interesting questions to you. So we as humans, we perceive colors, like I had said, that we only see the visible range of colors. And that is essentially due to the fact that our eyes have rods and cones are the ones that enable us to detect colors. So my question to you is, which creature can see the maximum colors in the world? Just you can maybe search for it. And if you have the answer, of course, you can give it. So which creature can see the maximum colors in the world? Is it humans, or are there creatures who can see even more colors beyond our apprehension? Cool. So now we will move on to the next experiment. which is the total internal reflection, and probably the coolest experiment that we will see, which has a huge amount of applications in our day-to-day life and the way we are communicating with each other. So for that, here I have a long cylinder of water and I have a laser pointer. Now, I'd ask you to just switch off the lights, please. Cool. So now I have this laser pointer. It's a green laser pointer. Now let's see what happens when I shine light through this tube. Cool. So as you can see, right now the laser is passing through and I have this reflected light. And now I'll start changing the angle. Whoa, what is this? Can you see the multiple reflections going on inside the tube? And what happens if I change the angles? Wow, this is mesmerizing.
You want to try with the red laser? The green is probably way too bright.
Yeah, the red is a bit dull, but of course I can give it a try. Give me.
Sure.
So let's try it with the green, red one and see how it looks like. Cool. So yeah, so we have the red one as well, but I think it's very, you won't be able to see it clearly.
You want to try adding a drop of milk?
Cool.
We just make the water a little dirty.
Yeah.
Adding some milk.
But we would need something to.
We don't have a stirrer right
No,
now.
maybe use a marker.
Yeah, just use a marker.
Oops. This will overflow.
It's okay. We just try it.
It's fine.
Let's see if the beam is visible in this.
Yeah, this might get scattered. Yeah, it's scattering. Scattering very badly. Yeah. So basically, when we are adding milk to it, so what does the scattering means for? First of all, I mean, we were able to see the entire path of the light. It was like so awesome. Then what we did is we added a bit too much of milk, and now we are unable to see the path of the light. Now, why is that so? So basically, when we are talking about optics, we talk about optics again. So study of light. No, it would be the sorry. It would be the same. See, even in the green as well, if you remember, we were seeing so nicely the path was being illuminated, but now we are unable to see that path. Right. Now, it depends upon the size of the scatterer. So scatterer is essentially anything that you see in the environment that scatters light. So basically light falls on it and it bounces back. And depending upon the size of the particle, we will have different regimes of scattering. So that like if we have very small scatterers compared to the wavelength of the light that we are incidenting on it, then we will have the Rayleigh region. If we have very large objects, then we are in the geometric region.
Okay, here you go with clean water again.
Cool. Oh, that was rhodamine water.
That's okay.
No,
no.
No, that was rhodamine water.
Water.
That's why it was not. Yeah. So here we are back again with the clean water, and we can again see the same PIR thing happening. Cool, right? Now, why does this happen? Let's go on to its experiment, to the explanation. Cool. Yeah, you can take both of them. Now, coming to the explanation part of the total internal reflection, what's going on here? So here we see a diagram. Again, we have two media. One is N1. N1 is the higher refractive index medium, and N2, which is the lower refractive index medium. We have a point at the higher refractive index medium through which we are incidenting light at different angles. So when the light is incidented at angle θ1, then it gets refracted at certain angle θ2, which is the angle of refraction, and it escapes into the air. Now what happens as we incident the light towards an angle called the critical angle. So basically this θ2 will keep on moving like here, then it will come here depending upon the angle of incidence, which are supposed to be equal. And then we encounter an angle called the critical angle, in which case the angle of refraction would be 90 degrees, and hence the beam would be parallel to your the two boundaries of the two media. What happens when we move towards an angle which is greater than the critical angle? In that case, there is no refraction anymore happening into the air. but rather we would have a total internal reflection. And as we know, in case of reflection, this angle, the angle of incidence, will be equal to this angle, which is the angle of reflection, right? So this is what happens when we have two media and when the light beam is traveling from a higher refractive index medium towards a lower refractive index medium. So based on this phenomenon, all this fiber optical communication has been developed. And there's another interesting experiment for the same, which Arnav is quite eager to show you all guys.
Yeah, you know, there is total internal reflection in a cylinder Ashish showed you. That's nice, but you want to do it at home. So all you need is a bottle. Can you turn it so I can see what's being shown? Yeah, all you need is a bottle. Okay, and what we'll do is we will make a small hole in the bottle. So I have a knife. I will. I just made a little hole in the bottle. So now there's a hole in the bottle. Now, of course, to fill this bottle of water is going to be tricky because if I fill it, all the water is going to go outside. So I'm going to hold the thing sealed with my finger and try and pour some water in the bottle. This you can do at home. All you need is a plastic bottle and a laser pointer. You know, there's no fun if you don't make a mess. The best experiments are where you can make a mess. Do it in your kitchen, bathroom, wherever. Make a little mess. Without a mess, it's no fun. Okay, I need some more water. Normally, I cheat and put a drop of milk, but last time I put too much, so I'm not going to risk it. Now, obviously, if I remove my finger, the water is going to leak out. But the nice thing is, here's the trick. Use the cap and cap this bottle. Now, I can remove my finger. And hey, the water is not leaking out. Now, that's another thing. Last year, if you remember, we did air pressure and things like this. But now you can see that I have a bottle here. Let's get rid of the milk packet. We don't need it. I'm going to need a laser pointer, the green laser pointer, and you'll have to be ready to switch off the light. Now, what I'm going to do is I'm going to shine the laser pointer from the back side of the bottle into this hole. Okay, where is the hole? There is the hole, and we will let the water run out. We'll slowly open the cap, and Suren uncle on the camera, you may have to go to the side to see this.
Bring it down. Bring it down.
Wait, there it is.
Yeah.
Can you see the light being guided in the water?
Yeah, look at this.
So this is total internal reflection that's happening inside.
Away from the hole? No, let the water flow and move it away. Move away the laser pointer. Yeah. Now bring it back.
If you look at it from the side, you can actually see the total internal reflection.
Yeah, you can see like from the side, you can see.
Yeah, you can see that the light beam is actually being guided by the water. And this is exactly how a fiber optic cable, for example, works. And that is what is enabling you to actually see this Chi and Y at home on the net, because all our internet traffic goes on fiber optic cables. Can we have the lights back again? So this is the way you can easily see total internal reflection at home. A very simple experiment, and it's fun because you can make a mess. There's nothing like making a mess. Kids love this. Okay, and remember, if you wanted to stop the flow of water, shut the bottle. If you want to stop the flow of water, shut the bottle. The moment you open the bottle, the water is going to flow. Okay, shut it, water stops, open it. Okay, you can play with this. Kids will love it. Okay, there we go. All yours.
Cool. So yeah, before moving on to the next part of the experiments, where essentially the first one we were focusing on the ray optics. So we had some questions from the audience that we can take up. Sure. So one of the thing was, is there something that is faster than light? Like, do we have anything that travels faster than light? Yeah. So now the answer to that is yes. The first one is kind of a cheating in our part, and the second one would make more sense. So let's come to the first part, which is when light travels, like I said, like when light travels in another medium with a higher refractive index, that leads to the slowing down of light. Now, compared to that, we have charged particles. When these charged particles travel through the same medium, their speed is not affected. Now, because of that, in that way, since the speed of light is slowing down, hence the charged particle velocity compared to the light speed in the medium is faster. And in that way, we can say that at that instance, the charged particles are moving at a speed of light, more than the speed of light in that medium. Apart from that, there is another way that another thing that we can say, yeah, it travels faster than light, and that is the expansion of the universe. Now we know that Edwin Hubble first said that a universe is expanding, and the rate of expansion is essentially for the galaxy which is 1 megapascal uh, years away from our Earth is moving at the rate of 70 kilometers per second. Now, given the fact, so again, the one galaxy which is 2 megaparsec away from the Earth, parsec, I mean, yeah, 2 megaparsec away from the Earth, it is moving at a rate of 140 kilometers per second. Now, the galaxy, which is about 14 billion megaparsec kilometers away from the Earth, is moving at the speed of light. Hence, those galaxies which are 14 billion megaparsec away from the Earth, or more than that, are essentially moving away at the speed which is greater than the speed of light. And the controversial thing is that we won't be able to see it because the light won't be able to reach our eyes since it is traveling at the speed of light. So this is these are the two instances in which we say that okay, there are things that can travel faster than light. Now we have another question in the comment, which is that I have heard two different explanations that change in the speed of light in various media. One is that the photons are absorbed and re-emitted. So that essentially depends upon the kind of experiments we are conducting. Like I said, that light has multiple personalities that it shows depending upon the experiments you are conducting. So when we are considering ray optics, in that case, we are looking into geometrical optics, and in that case, we do not consider the light to be a wave. When we come to wave, in that case, we are considering the Rayleigh optics, or we are comparing objects which are of the order of the wavelength or smaller than that. And then there is the regime in which we are considering light to be particles, in which case we are actually describing systems in which we are dealing with only few photons. So that is why we would have different explanations to similar phenomena. And that's how we connect them. Right. Now, we will now move on to the next part of our this segment, which is going to be the wave optics part, and which will be taken care of by Aprajit. Thank you.
Hello. Thank you, Himadri. Yeah. Hi. Hello, everyone, and welcome to this Chai and Mai session. And I would like to thank Himadri for the first part, where she showed a lot of fun experiments pertaining to like ray optics, where we looked at refractive index, reflection, refraction, total internal reflection, and so on. Now I'm going to move on to a completely different property or concept with respect to light, which is very important in our day-to-day lives. What it is, effectively, what I'm asking is, what makes or does light dance around? Is it like a wave, like water waves? You see water waves. If you play around with water or go to a sea, throw a pebble in, just like that, we know that light is also a wave. Can we actually see that in experiments? That is what we're going to look at. And another question that I have, a major concept related to this is, if you take two beams of light and you combine them, what happens? Like you might know about Ramesh and Suresh from the different ads that you see, basically like that, if you take two beams, they come together, when they interact with each other, does the resultant wave become stronger, or do they like fight with each other, and can they kill themselves and destroy each other? Can we see all of that? Or does that really happen? That's what we're going to see. So the first setup, first let's look at a demonstration, and then we'll move on to an explanation for this. So the first setup, what we have here, if you can see, we have a laser pointer which is mounted on a base, followed by a aluminum foil, which has basically slits cut using a knife. So this is also something you can do in your home. You just need to take a foil, and then in the foil, take a knife, take as sharp a knife as you can. You can also have a blade. You take the knife and you basically try to make two slits which are close to each other, not very far apart, very fine slits using the knife, and not very far apart. And then you take it and you can either stick it to a screen or somewhere with a hole in the middle. That's what we have done here. We have a circular aperture with the foil stuck to it. So if you look at it from this side, what you can see is you have different slits, basically different slits which have been cut using a knife. And what we are doing is we are basically shining the laser on the slits. So, okay, so what do we expect? So, yeah, so what do we expect? Generally, okay, let's just see what happens now. What do we see? Lights off. Wow, what is this? Maybe we can see the entire big pattern. What is this? We see an amazing pattern that the light has made. We see a very bright spot at the center, followed by like dark, bright, dark, bright, dark, bright pattern, which goes on either side of the central maxima. And there's more interesting thing. The central bright spot is not just one bright spot. It also has subdivisions in it. If you zoom closer in, you can actually just, Ankit, you just slightly improve the contrast. Yeah, I think we see it.
Yeah, you can see it.
Yeah. So if you actually focus closer, what you see is the central maxima also has a lot of these tiny bright dark pattern which goes all across. So what is happening? How is this amazing pattern being generated? Yes, lights. How is this amazing pattern being generated by light? So to understand that, I would like to talk about a couple of basic concepts with respect to the light. The first thing that I want to talk about is called the superposition of light. What it means is, if you take two light beams, this is one, and this is say two. And now if you combine these two light waves in such a way that the crests are exactly on top of each other and the troughs are exactly on top of each other throughout the wave, what happens when you add this is you get a resultant which is stronger, which has an amplitude which is going to be twice. So if you say that this amplitude is A, the amplitude of this is going to be twice of the input wave. Similarly, if we take two waves, but then we displace one with respect to the another in such a way that the crest of one meets the trough of another, and the trough of one meets the crest of another. So what it means is when you add these two, this is going to be a positive amplitude added to a negative amplitude. These will combine to give 0. Similarly, negative plus positive will give 0. And the sum is going to be 0 throughout the wave. So the first one is called constructive interference, where they both add perfectly together to give the maximum signal. The second one is called destructive interference, where they combine to give you a null signal. And these are the two extremes. You can obviously have the gap between them to be different in between either of these two extremes, in which case you get a wave which is going to be between the maximum and the zero. So that is the first, which basically says that if light is a wave, it can combine in different ways to give you constructive interference and destructive interference. Now, second thing is, now how do we know that light is really behaving like a wave and not, it's just not made up of particles? Now, if you look at this schematic, if you consider the input laser beam just to be a collection of particles and they interact
You are muted, Aprajit. Your mic is off. Can you hear me, Aprajit?
Okay.
Yeah, now it's coming. Yeah.
I think you're back.
Yeah, it's coming. Go ahead.
Okay, yeah, sorry about that. So as I was saying, if you consider the input light to be a collection of particles which interact with two slits, what you would expect on a screen would be just two lines which would correspond to where the particles will. So particles, you consider that they'll move in straight lines from the slit and reach the screen, and it will form two patterns, basically just two lines which will correspond to where the slits were. But what we see is much different. What we see is rather something which can be explained using this diagram, where we consider that light is a wave. Here, these lines correspond to the wavefront, where basically the different light waves at different points, their crests meet each other. So here, when they interact with each slit, from each slit, you have these waves which are coming, and they will combine on in the screen. Now, when you look at like the central point, we saw a very bright spot at the center. Why is that? Because basically the central spot is equidistant from both the slits. The distance of the central spot is same from the both the slits. So as they're traveling from the slit to the screen, they will have the same phase. Phase is basically when the crests match each other and the troughs match each other. That is when they are in phase, and they'll have exactly the same phase at the center. And when you go slightly away, the beam that's coming from this slit has to travel more distance compared to the wave that's coming from this slit. So because of that, as it's traveling, it gains an extra phase, because of which it can end up being out of phase, where the crest of one meets with the trough of another. That's why we can get a dark spot here. Similarly, at different points here, again, you can have them being again in phase and then again out of phase and so on. That is how you can explain this interference pattern. So that was like the first part of which is trying to prove that light is not just like a bunch of particles, but it behaves as a wave as well. We have another experiment which demonstrates the same principle of superposition of light and interference. Now, this might look a little complicated, but what this is called
a very, very historic experiment. Right?
This is a very historic experiment. This is called the Michelson interferometer or Michelson-Morley interferometer. And the historic part comes from the fact that this was the experiment which proved that Earth, whatever space is surrounding the Earth, it's not made up of any material like ether, which was thought of back in the days, but rather it's all vacuum. And this is the experiment that actually proved that it's all vacuum. So what is this experiment? Let me explain the setup first. So what we have is, we have a laser again here, followed by a lens. The lens is basically going to expand the beam like a magnifying glass, followed by a mirror, which is going to send it to this guy. What is this? This is called a beam splitter. What this does is it sends one part of the beam straight through the beam splitter and it sends one part reflected through the beam splitter. So there'll be one which will go left and there'll be one which will go straight. Now, here again, there's one mirror and there's another mirror here. So they will reflect off the mirror and come back to the beam splitter. And after they come back, they basically interact with each other, and that's what we are trying to see on a screen. Let's look at the pattern. Wow, what do we see? Do you see circular pattern? Do you see rings of different intensity of like bright, then dark, then bright, then dark, then bright, then dark, concentric circles of bright and dark fringes or dark spots onto the paper? This is also an interference pattern. This is formed in the Michelson interferometer. And how does this happen? What is happening here? The principle is again same. It is of waves interacting with each other, and when they interact in phase, when they add up constructively, you get the bright spot. When they add up out of phase, you get a dark spot. And this setup is in such a way that in the center, you have the waves interacting in phase, and as you move slightly outside the center, you have the first minima or the first dark spot where they are out of phase, and then again in phase and again out of phase and so on. Now let's see what else we can do in the setup, how we can change the pattern even more. Let's play, let's have fun. So one second. Just keep looking at the pattern. Maybe move it closer.
Just switch on some lights. Switch on some lights. Yeah, that's actually not. Yeah, much better. Yeah, okay.
So right now you can see the concentric circles, the bright, the dark, bright, dark. Circular fringes is what we call them. Now let's see, let's play around with it. Ankit? You can see that the pattern is moving here. Earlier, it was nice circles which were centered. Now it has moved to the right, and what we see are just like one side of the circle. And as we keep on moving it, this will move from circular pattern to actually straight or curved patterns. It's no longer circular pattern. And how did we do that? What we are basically doing is tilting one of the mirrors of the interferometer. As we tilt the mirrors, what happens is the waves, as they are overlapping, the overlap slightly changes. And because of that, the regions of constructive and destructive interference changes, and we get different kinds of patterns. Yeah,
I hope people can see them on the screen. This is actually something which your naked eyes are probably the best at looking at these patterns. It's kind of difficult to capture it using a mobile phone camera, but I hope you could still get an idea that the fringes were shifting.
And this experiment is very important, and it's basically what people do is they look at the fringes and they you can put different materials in one of the arms and try and explain, try and get properties of that material by looking at how the fringes shift and how the fringes change as a function of what you add to a particular part. There's one more interesting thing here in the pattern. If you see that maybe lights off one of them. Okay. Now, if you look at the pattern, it's not static. It keeps on vibrating. And yeah, so the pattern is not static. It keeps on moving. It keeps on jittering. Why is this happening? Now, this experiment is a very sensitive experiment. And what we have is we have the setup on any table. but this table is not vibration free. There can be vibrations on the table which are coming from different places, and these can actually move one of the parts of the interferometer a lot more than the other part. And if you actually try to tap or bang on the table, you will see that the fringes shake a lot more than usual. So using this, you can actually even measure vibration levels that are there in a particular place. You can just look at how the fringes vibrate and change. And from that, you can get an idea of what kind of vibrations are there, what levels of vibrations are there in a particular. So that was the first part where we are trying to give you an idea that light is not just a bunch of particles, but it behaves like a wave. It superposes, it interferes, and gives you different kinds of patterns. The next thing that we are going to look at is going to be called diffraction. What is diffraction? It is basically you have a light wave and then it interacts with, say, a material in front of it, like a slit or like an aperture or opening. What happens to it? Like if it faces any kind of boundary or obstruction, what happens to it? Does it travel in straight lines? Does it do something weird around those boundaries? That's what we are going to investigate. So the other green laser. Okay. So what I'm going to show you, again, I have two lasers. Both of them are green lasers. The only difference is that one of them is like plain. The other one, I have a hair. You can just take a piece of hair from your head, and then place it right in front. So I don't know if this can be seen on camera. Can this be seen on camera? Okay, so we basically have stuck.
Kind of difficult. Okay, you have to believe us.
Okay.
No, it's tough to see.
Yeah, I guess it's
Very
too
tough to
thin.
see what
Very tough to see what the hair is. But basically, one of them has a hair stuck to it in front of it. So let's see what happens to the thing. So generally, if you consider like light, so this is without the hair, and this is how it looks. It's, yes. So you have a very bright spot at the center. That's the laser. That's where the laser is shining. Now, my question is, if you put a small wire or hair or wire, anything in front of it, what will happen? Will you see a shadow? Like if you take a torchlight and put a pencil or a marker in front of it, what you might say is, oh, I'll see a shadow. I'll see a shadow of the pencil or a marker. Similarly, I take a laser and I put a small wire in front of it. Will I see the shadow of the wire? What will I see? That's what we look at. Now I'm going to take the other laser with the hair and I'm going to shine that.
It looks like there's a a horizontal line.
We have a horizontal line. We have a huge line, a long line. And not just that, we see.
One sec, just one sec. Just want to make sure that we've lost the video. Just a second. Okay, we are back. We're back. Okay, can you go closer?
Yeah, I'll try.
So earlier we only had the central bright spot. Now, as soon as we put a small hair onto the path, yeah. So now,
Yeah,
not this much. So as soon as we put a hair in the path of the light, what we see is we see
Some slightly far away so that's it. will be good on some wall.
Basically, you can see bright, dark, bright, dark, bright, dark in this region.
It's too bright. Can't control the brightness of the
We have a red laser, no? We can probably try with the red as well.
Red laser is
Or
very bright.
rather, yeah, that's better.
Yeah, better. Another flame. Yeah, this is probably better. You can see on the wall that there is the central spot is bright. It's not dark. It's bright, even though there's an obstruction there. And there are bright, dark fringes equally spaced that you can see when the light is hitting a hair and then going ahead. What's happening? The light is bending around the hair.
Exactly what really is happening. And also another interesting thing is, earlier, as I was saying, if you take a torchlight, you put a marker in front of it or any obstacle, you'll see a shadow of the marker. But here, if you look at the central spot, you don't see any shadow of the hair. Or if you put a wire, you can take any wire and try this experiment. If you have a laser pointer, you will not see the shadow of the object if it is very small, if the object is very thin. Why does this happen? What ends up happening is called diffraction, and what this is bending of light around thin objects. So I have a small schematic here. Again, we have a comparison. If we have a particle beam here, and if we have it go through an aperture, or in this case, it's the opposite of an aperture, it's an obstacle in the middle. What will the obstacle will do is it will block light wherever it is, and wherever is the aperture or gap, light will go straight through it. That is if you assume a particle picture. Now, we know that light, after looking at the interference experiments, we know light is also behaving as a wave. Now, because that happens when it interacts with an obstacle or an aperture, it actually bends around the obstacle. Now, this is the bending that actually leads to the diffraction pattern, or the pattern you just saw. What is happening is the wire, as the laser is going through it, the light which is coming from the right side of the wire and light which is coming from the left side of the wire, these are bending, and they are then interfering on a screen which is kept far off. Now, at different places on the screen, this interference coming from the two sides of the wire either add up constructively or destructively to give us that diffraction pattern of bright, dark, bright, dark, bright, dark. And this is again a schematic which is explaining the same thing. We have the beam which comes, interacts with a slit, and it goes through, and then what you see are bright, dark, different spots onto the screen. Now, the question is, let's look at what happens to this pattern as we change the gap between, like if you take a slit, if you change the gap between the slit, what happens to the pattern? So before that, let me show what we have here. Again, what we have is a laser pointer here, followed by sorry about that.
No, okay.
So we have a laser pointer followed by aperture here. This aperture is just a single slit which is there. And here we have a knob which allows us to control the gap between the gap in the slit.
The gap.
So here, if you look here, I can basically make the gap small. Now you don't see anything. Now I can make the gap bigger and more bigger and bigger. So this basically allows me to control the gap in the slit. And by changing the slit width, we are going to see what happens to the diffraction pattern.
Okay, lights off.
Yeah. So we see. So as you can see, we again see a central bright spot followed by a series of dark, bright, along on the left side and also on the right side. Now let's change the slit width. Right now, I'm going to increase the slit width. Can you see them moving closer in and closer to the central spot?
So when the slit is very big, you don't see any of these fringes at all.
So when the slit is very big, it's completely open, you don't see any fringes. It's as if nothing is blocking it. But when the slit becomes smaller and smaller, you start seeing these effects. So I'm reducing the slit width slowly and keep.
There we see fringes.
We see fringes, and now they are spreading more and more, going farther away. And then after a point, the slit just fully blocked the beam. So again, what is happening? What is really happening? So basically, the idea is that there is a particular size of the aperture. Like, what size of the aperture really matters here? What can we compare to with respect to the property of light? So we know from what Himadri had told earlier that light is a wave, and waves have a property known as the wavelength of light. So the idea here is that the wave nature of light becomes more and more visible or apparent when it meets slits or aperture which are comparable or close to the wavelength of light. And here we are using red lasers, which are close to 650 nanometers. So any slits which are close to 650 or like orders of magnitude close to 650, close to a micron, you can take a micron slit or a few micron slit, you will be able to see this pattern. But if you take a slit which is big, like a millimeter or centimeter big slit, you will not be able to see the pattern. We have another shape of the fringes. Again, this is diffraction. What we have is a laser pointer again, and we have two sets of wires, which are again very thin wires, which have been stuck to this aperture. What we are going to do, we are going to shine the laser at the central spot and try to see what happens. Yeah. So here again, like if you see two lines. You see two lines, each line has the diffraction pattern corresponding to it. Why is that happening? Again, because there's a crosshair. Both the horizontal and the vertical crosshair will correspond. They'll each diffract the light and give you the pattern corresponding to them. And you get this nice crosshair pattern with those bright, dark, diffraction pattern, diffraction fringes in them. So, yes. So that was the basic idea of, or the concept of diffraction, where we are trying to say that light behaves as a wave and light diffracts along corners and apertures which are comparable in size to the wavelength of light. And if you have like a laser pointer, you can try it out easily. You can try the experiment with hair. You can try the experiment with any thin wire if you can find. And another thing you can try with regards to slits, if you don't have slits, either you can make slits in aluminum foil, or you can even take staplers. You can take two staplers and then keep them very close to each other and make a small slit around it. So you can just break, like if you take a stapler, you can just break it into two pieces and then hold them very close to each other. That will also act as a slit. And using that also, you'll be able to see these nice interference and diffraction patterns. And with that, I would like to end my part and say thank you. And thank you for being here and seeing all these fun experiments. I would like to hand over to Arnab.
Okay, those experiments were fantastic. I mean, those are, you can always look at these optics experiment for hours on end. They just look so fascinating. But I'm sure the audience has questions. So Himadri and Rajit and the team, okay, I can see that a lot of people are crowded around the computer. They're probably trying to answer questions which are coming in online. But let's see if we can take a few of them and answer them on air live. So maybe what I'll do is the two of you come here. I will read out the questions and you guys can try and answer them or do some quick experiment to show what they are. Okay, so let's do that. So let's see if there are some interesting questions on YouTube and Facebook. So first, let me ask the people who are monitoring Facebook, are there interesting experiments on or questions on Facebook that we need to answer?
No, not really.
Okay, so let's see. There's one very interesting question on YouTube from Joseph who asks, are these interference kind of patterns, do they have use? For example, can you look at different kinds of tissues, or do they have some applications in medicine or some other areas where you use interference?
Yes, so definitely. As I was trying to tell you in the microsense interference part, what we have is we have the two arms of the interferometer, for example.
Arnob, we can't hear. Yeah.
Yeah. So if you
No, still I can't. I can't hear.
arms of the microsense interferometer,
Aprajit, if you.
and put them together. Now, if in one of those arms you place any material, say,
I can't hear you for some reason. Is that thing on? Is the blue light on?
Arnob, your voice is much clearer than.
Okay, because you've taken the wrong one. Sorry, no wonder. Okay, sorry about that.
yeah.
You used the wrong mic. Everybody roams around with these headsets these days. It's such a problem figuring out which one is which. This is after Zoom fatigue, it's the next thing. Headphone confusion.
So in interference, we basically have two laser beams which are interacting with each other, just like in the Michelson interferometer, we have the two arms of the Michelson where we have the beam which is split into two parts and they interfere on a screen. Now, if the arms are have the same length, the path in the two arms are exactly equal, you get these nice circular interference patterns. Now, if you want to study properties of some particular material, what you have to do is basically place, like for example, you can take a thin glass or water or any tissue, as you are saying, you can place it in one of the arms of the interferometer, and as light passes through this tissue or any other material, it will gain an extra amount of path. And because of that, it will gain an extra amount of phase. And because of that, when you look at the interference pattern, you'll see changes in the interference pattern as soon as you introduce the new material in one of the arms. So by basically studying the changes in the interference pattern, you can infer what are the properties, optical properties of these materials.
So a very few applications have been recently demonstrated, like the detection of gravitational waves. So they use a very big interferometer, 4 kilometer long. So it can be used there. It can also be used. You have seen in movies 3D holograms. So like in Iron Man movies, right? You see everything in the famous light shows. So 3D holograms you can create with interference patterns. So there have been various applications, and you can use it for all. Yeah.
Okay. I hope you can still hear me. I'm going to shout so that the microphone picks it up. A very simple question: can two waves with different frequencies interfere?
So yeah, so they can interfere, but not in space. So like we have demonstrated you interference pattern in space. So there you need a monochromatic wavelength, a single particular wavelength that can interfere. But if you have two different frequencies, then you have a beating signal. So you can interference in time. So there are interference patterns in time, space, and in frequency. So with two different frequencies, you can have interference pattern in time. So there you will have fringes as a function of time. You will record on the detector maxima, minima as a function of time. So yes, you can have interference with two different frequencies as well.
Earth was what was it, surrounded by vacuum or whatever you said, the absence of the ether. It just explained the historical significance of the Michelson star.
Yeah.
So again, like as I was saying, that if you put any material on one of the arms of the Michelson interferometer, that will lead to an extra path difference that is added. So now if, for example, there was vacuum in the air in the surrounding the Earth, there will not be any extra phase added. But if it had ether, for example, it would have an extra phase that is added. And when you look at the interference pattern, you don't see any difference. So what these people saw historically was the fringes did not really change because of the extra material.
And that extra phase, basically, if there have been an ether medium, so basically light will be traveling in that particular ether medium, and the ether medium will have a certain velocity with respect to the reference frame, and that the total velocity which the mirror will observe will be c plus v or c minus v. That v is the medium, the velocity of the ether medium. So basically, the scientists didn't observe any of these fringe pattern shifts, so they concluded there are no ether medium.
Okay, before I take the next question, I'm going to ask Ulhas, who is in Kalyan and looking outside his window, do you think you're seeing any sun? And do you think you're going to be able to show us live the zero shadow today, or is it too cloudy? While he says that, looks out, there's a very nice question from Arpita, who's asking, when you put the hair in front of the laser, a vertical hair gave you a horizontal line, and when you had a cross thing, it, why is it like rotated by 90 degrees?
Okay, so basically what happens is if you have a vertical hair, okay, let me just take a pen to explain. Like,
Chalk and board.
okay. So basically, if you have a hair and then light, or maybe draw here, like this is my hair, and if light comes and shines here, what happens is light on this side and light on this side will go and interfere on the back side. Now we have light which comes, and then think of it like a different plane, and you have a screen here. Basically, the part on this side and this side will come and fall on the screen, and different parts which are again having, like if you look at in the horizontal line, like as you move farther away from the center, the beam that is on the left of the wire and the beam that's on the right of the wire, they'll take different amounts of time to reach. Now, if you look at just like the vertical, like the hair is vertical, and if you just look at a point which is vertically up from the center, beam on both sides of the mirror will travel the same path everywhere along the horizontal or vertical line. But it's on the horizontal line that parts of the light on the left and right of the hair will actually travel different amounts of path. And because of that, you have this phase difference, which leads to the pattern. So always, if you have a vertical hair, the diffraction pattern that you will get will be horizontal. If you have a horizontal hair or a piece of wire, you'll get a vertical diffraction pattern. I hope that.
Can I sort of butt in and answer something related to this?
Yes.
So actually, if I may come in here and keep some space, of course, this diffraction from things being 90 degrees away has been a very important concept in our understanding of, for example, the structure of DNA. DNA is a double helix. And the way we understood its structure was because of X-ray diffraction. For those of you who can access the net, please look at photo 51, one of the most famous photographs in history, where people looked at a helix is like a spring, right? So if you look at a spring, it's like the shadow of a spring. It will be like different wires which are like this, one set, and there'll be another set like this. And they found an X-shaped pattern. And from the X-shaped pattern, they knew it was a helix. And then looking at, which of these, you saw these dark light patterns, they could actually see and come back and find out what the spacings were in all these cases. So by the way, there was another question. is the spacings in this dark light related to the thickness of the hair?
Yes.
Because you know, when you change the slit thickness, the pattern was changing.
Yes.
So can you figure out the thickness of the hair from your pattern?
Yes. Yes, you can. So like thickness of any wire or hair or an aperture, you can find that out by looking at what the diffraction pattern is, what are the gaps between the bright and the dark fringes, or two bright fringes. You can find out what the gap between them is. And you also need to know what the distance of the screen is from your wire. So like there's a simple formula which I can just write here, using which you can calculate if you have like a laser and a hair. If you try this out at home, all you need to do is have, is this visible? Yeah. So you take the wavelength of light. For our case, for a green laser, it's 532 nanometers. If you use a red laser, it might be 650 nanometers and so on. You take that, you multiply it with D, which is going to be the distance of the screen from your wire. So it might be, say, a meter, wherever you keep your screen away from the wire. And you divide that by the small d, which is going to be the distance between the fringes on the screen. So between any two consecutive bright fringes, if you can measure what the gap between them is, you take that and you plug that in for the small d. And if you calculate this parameter, this will give you what the thickness of your hair is. So you can try this out at home and actually calculate it and let us know the values that you get. It's a really fun experiment you can try. And you can calculate the thickness of a wire, the thickness of a hair, or anything.
Okay, let me see if there are any more questions.
An alternate thing is also like, if, for example, if you use a laser whose wavelength you don't know, but if you know a wire whose thickness you know, again, you can use the same formula. You just plug in the thickness, you plug in the capital D and the small d, and you can find the wavelength of your laser out as well.
Yeah, I have one question.
Yes.
Can you explain it? So in the diffraction pattern, you saw that the wire is symmetric in this plane, right? Yeah. So the wire is symmetric in this plane.
Can you repeat the question?
Oh, okay. Okay. So the question is that, so if you have a wire like this,
Yes.
so if you're shining the light from here,
Yes.
and what type of, will you see the pattern in this direction also? You can also see the pattern in this direction, because this is symmetric wire.
Symmetric as in
Symmetry, it has cylindrical symmetry, right?
yes, yes. So
Is it side like this? You know, the pattern are forming like this, right?
yes,
Yeah.
yes.
Can we see the pattern forming like in this direction?
I can take the question.
Yeah, sure.
So yeah, so depending upon the symmetry of the object, we will have the scattering profiles will be defined. So in case we are taking a symmetrical wire, as in this case, we have this cylinder, and right now we are focusing our light in this direction, and hence we are getting a fringe pattern, which is, say, in this case, we get this horizontal fringe pattern. But if we take it in the opposite direction, say perpendicular to this plane, so instead of getting this horizontal thing, we will get, since again the cross section of it would be circular, and hence we will get a circular kind of fringe in this case.
Okay.
So the scattering profile will be like that. So depending upon the symmetries of the objects we are getting, we can define how the scattering profile will look like.
Okay, I think there are no more questions. Remember, if you have questions, you can always send us an email. Our email address is outreach, outreach @tifr.res.in. Can one of you write it down over there, please? outreach@tifr.res.in. Just get a clean board. No? Meanwhile, let me tell you what's happening 2 weeks from now. 2 weeks from now, we're going to continue with these optics experiment, because we had just so many of them, we just couldn't do it today. We have more fun stuff, things called other properties of light, polarization of light, for example. We will also look what happens when the light intensity increases, when you have high power lasers or something, and we'll do some more fun experiments. Till that time, remain safe please wear a mask if you're going outside. And unfortunately, we are hearing from our friends in Kalyan who are watching this that there is really no sun outside. So we cannot show you the zero shadow day. If July 27th happens to be clear, take a shot again. If not, have a nice weekend and see you again at Chai and Y. And let's thank our entire team, Himadri, Prajit, Kiran, who's there, Ankit, whoever, wherever Ankit is there, everyone's who has helped. Okay. Thanks a lot. Stay safe and see you again at Chai and Y. And email address is outreach@tifr.res.in.